Yeah, am I loud and clear?
Yep, sounds
Yeah,
good.
we can hear you.
Okay, great. So good afternoon or good evening or good morning or good night, wherever you are. Let's get started on the, like I said, the third lecture in SO81, which is going to be about OS organization. And the topics for today are four things that I want to touch on. One is isolation, which you'll see is a driving design goal for OS organization. I'll talk a little bit about kernel and user mode as a way of isolating the kernel from, or the operating system from user applications. Then I'll talk about system calls, which is a way for user applications to basically transition into the kernel so they can ask for services. And we'll look a little bit how this all is instantiated in a simple form inside of x86. So that is the plan for today. And just to sort of remind you where we were after the first lecture, the picture sort of in your head that you should have in your head is, there are processes like the shell, like echo, or whatever, find, whatever some of the utilities that you implemented. They're running on top of an operating system. And the operating system abstracts some of the hardware resources, like a disk or a CPU, and basically the interface between the operating systems and the shell is typically referred to as a system call interface. And the interface that we've been looking at is the Unix interface. And here what we see is so that was roughly actually with that Unix interface you've been playing around in lab 1. Where in the util lab where you used the system call interface or the Unix API to actually implement different sets of applications. And so lab 1, the util lab was mostly focused on sort of using this part of the design picture here. And what we're going to be doing now in this first lecture or this lecture and many subsequent lectures, we're going to really look actually how the interface is actually implemented. And in fact, almost all of the semester, we're going to be spending time on figuring out actually how to implement the interface. And so this is going to be the first lecture of that kind of style. And unfortunately, a lot of you asked really great questions over email or submitted great questions to the website. And we won't be able to go into great amount of detail immediately in the sort of first lecture that takes an inside look of the operating system. So we're going to touch on a lot of different things. But many things will become more clear in subsequent lectures where we're going to explore them in more depth. But nevertheless, if there's something unclear, feel free to interrupt and ask a question. And maybe just to start off, before actually going any further, let me ask you a question and sort of get the question and answering hopefully going. And ask you, like, what is the sort of most interesting thing that you learned from the util lab? And I'll start by answering that question myself. One of the things that actually surprised me after writing and doing the util lab is that I use Xargs a lot more frequently than I used to do. I had another way of doing basically the same thing as Xargs, set of commands. And after actually doing the Xargs lab, I was just like, oh, that's much more convenient actually to use it in that way. And so since then, I've been a much more aggressive user of Xargs. And I'm just wondering, what the experience has been for some of you. And so maybe I'll call out a few names, and maybe you can unmute your microphone then and sort of say a little bit about like your experience with the util lab. So let me pick some people. Andrew, you. Andrew, are you online or listening?
The most interesting thing for me was just the pipes, like how to write concurrent programs.
Good. Had you done any sort of pipe programming before, or is it the first
No,
time?
I haven't. I've like seen concurrent stuff, but I haven't seen like OS level pipes before.
Okay. How about Elizabeth Weeks?
Yeah, I'd agree with that. I also thought that the OS pipes were super interesting, and like the primes example specifically was cool to kind of figure out and realize that like I needed to close certain pipes and just like how they kind of related to each other.
Yeah, presumably you did find the pipes of the primes a little bit harder than you might have thought. Which surprises me every time. A little bit tricky to get it right. Jessica Shi.
I also thought the primes exercise was the most interesting.
Good. Did it take you a lot of time, or was it not too bad?
It took me more time after I realized my initial implementation wasn't actually concurrent. So it was interesting to think about like what the differences are there.
Okay. How about Robert Murphy?
Yeah, I think that my experience was really just I found it really challenging to program in the original way that was set up. So I actually created like a bunch of helper functions that wrapped around things. So that's, I guess, what I did.
Okay. Anybody else who has sort of any piece of wisdom? Amanda, go ahead.
I kind of liked it and found it surprising / cool that S2D in and S2D out are just filed descriptors themselves, 0 and 1.
Yeah. Good. Yeah, and the X36 doesn't hide that from you at all. At least in the normal C library, that's a little bit wrapped up in an interface, but X36 doesn't hide it for you. But in the end, it boils down indeed to just file descriptor 0 and 1, and 2, I guess, for standard error. Good. Alexandra.
I guess one thing I was surprised about was also from the primes problem. I had this bug that I spent hours on, and the thing was that I didn't realize that actually there were, whenever you were opening a pipe and then calling fork, then basically there would be 4 ends to the pipe, because that pipe, it's kind of goes both to the child process and the parent process, but I was only closing 2 of those.
Yeah.
So yeah, that was
a common problem.
it made sense, but for some reason, because especially the textbook says that when you fork, all of the open file descriptors get copied, but I didn't think about it then.
Yeah, no, it's hard to. I mean, there's a lot of details in that interface, and the only way to get actually really familiar with it actually is to program with it and then experience it. Good. Well, good. I hope you enjoyed the lab, and of course, I hope you'll enjoy the subsequent labs too. So the lecture for today, in some sense, is really partially to help you to get going on the Syscall lab if you haven't already started. And so again, feel free to interrupt and ask questions. Okay, so the first thing I want to do is talk a little bit about isolation and why it's important and why we might care. And the basic story is reasonable simple. We have multiple applications here. We got the shell, we got echo, we find, and it would be great, correct, that if you had a bug in the shell, or for example in your primes program, that it actually didn't affect any of the other applications. Particularly it would be bad, for example, if it affected the shell, because probably the shell you're using to actually kill the program if something goes bad. And so you want sort of strong isolation between these different applications. And similarly, the OS is sort of the servant, for all the applications. And you would like it to be the case that, if, again, you make a bug in one of your util programs, that actually the operating system doesn't crash. For example, you pass some strange argument to the operating system, it should be the case that the operating system handles that well. And so again, you would like to be there's sort of strong isolation between the applications and the operating system itself. And one way to think about this a little bit is ask ourselves the question, what would happen if there's actually no operating system? So like, consider some strawman design where there is no operating system. Or you can think about it as the operating system basically just being a library, sort of thinking of, in terms of Python, maybe just import OS, and import OS basically loads the whole operating system inside of your application, and that's then the programming interface you use. So if you think about that, sort of way of thinking. So let's say we have the shell here, maybe it includes the, the library for the OS, and maybe we already have some other application, Echo. And then basically, these applications, if there's no operating system really, would directly interact with the hardware. Right? So for example, they would actually see, there's a CPU core, there's another CPU core. And maybe there's a disk, and then we interact directly with the disk blocks, and maybe there's memory, and then we directly interact with the memory of the machine. And so there's like no layer between, no abstraction layer between basically the applications and the hardware. And it turns out that it's just not such a great design for isolation. And you can see how isolation might be broken. Let's assume, for example, that one of the goals for the operating system is run multiple applications. And so that has to be the case that once in a while, we'll switch from one application to another application. Let's say the hardware has only one CPU. And so we're running the shell, say, that one CPU, but periodically, other applications should be able to run too. Well, we have no operating system, to do it for us. Then the shell basically has to sort of give up, the CPU once in a while, and sort of be a nice person and say like, well, I've run for a little while, you get a chance to run. And this sometimes is called cooperative scheduling. But that's not so great for isolation. For example, what if, some function in the shell has an infinite loop, and therefore it will never actually give up the CPU. And then no other, applications could run, including maybe the application that would like stop or kill, the shell. And so we basically don't get any sort of form of enforced multiplexing. And that's something that we'd like to have, where no matter what the application does, it will be forced to give up the CPU once in a while so that other applications can run. And similarly, if you think about the Strawman design, we have, there's like physical memory, right? And I drew the picture here as sort of the application sitting on the top of the hardware, but there's physical memory, and basically the text and the code and the data for these applications actually sits in physical memory, right? So here's memory, and here's maybe, the part of physical memory that's used by the shell, and here's maybe the part of the physical memory that's used by Echo application. And so you can, and again, what we see here, if we use like simplistically like this, there's sort of no boundary between these two guys. For example, if Echo stores to a location that, for example, belongs to the shell, like location 1000, and writes a value there, whatever X, then it would just overwrite the physical memory of the shell memory. And so that be pretty undesirable, right? Because then a bug, an Echo could actually percolate into the shell, and it's going to be very tricky to debug and that kind of stuff. And so this basically again gives us like no strong isolation. What we like is to have memory isolation, so that one application cannot overwrite the memory of another application. And so one reason, or probably the main reason to actually have an operating system is basically to enforce both that multiplexing and to enforce strong memory isolation. And if you didn't have an operating system and the applications were directly interacting with the hardware, then it would be very hard to achieve that. And so this design of basically operating system as a library is not a very common design. You may see it in some real-time systems where basically the applications trust each other. But in most other operating systems, there's an operating system that really enforces that kind of isolation. So if we look a little bit now at the Unix interface from this perspective, then we see that the interface actually is carefully designed so that it actually is feasible to implement that enforced isolation in terms of multiplexing, in terms of physical memory. And the way that it's sort of done is that the interface basically abstracts the hardware resources in a way that then it makes it easy to actually do, or not easy, or it makes it possible, to provide, this strong isolation. And maybe to give you some examples. So processes, we've seen them, like the things that are created by fork. They're not, literally a CPU. right? I mean, the sort of, but they correspond to like what a CPU is. You know, it allows you to run computation. But because the application cannot directly interact with the CPU, but only for this process abstraction, the kernel sort of behind the scenes can switch between processes. So instead of having direct CPUs to manipulate or given to the application, the operating system provides processes that abstract away the CPU itself, so that actually the operating system can multiplex one CPU or multiple CPUs among multiple applications. Similarly, if you think about exec provides a memory image. Armando, yeah, go ahead, ask your question.
One question about like processes sort of like abstracting the CPU. Is it that one process uses part of the CPU and another process uses a different part of that CPU, or a different CPU if it's like a multi-core? Or like,
yeah.
What do you mean by processes instead of a CPU?
Yeah, okay, so I really mean one CPU abstracted away into a process. So, okay, so the way to think about it is the RISC-V core or RISC-V processor that we're using in the lab has actually 4 cores. And so you can run 4 processes concurrently or in parallel, one process on each core. And what the operating system does is, let's say you have 8 applications or 7 applications, it will take some core and time multiplex it between different processes. So for example, it will run, one app process for 100 milliseconds, then stop, unload, that process out of the CPU or out of the core, load in the next application or the next process, and runs that for 100 milliseconds. And it just enforces that no application can run or no process can run longer than 100 milliseconds. And we'll see exactly how this is done in a couple lectures, but that's sort of the basic idea.
Okay, but multiple processes cannot use the same CPU at the same time.
No, it's time multiplexing.
Okay.
So you run for
Okay.
one for a while, then you run the next one for a while.
All right, thank you.
Okay, so one way to think about exec is that it actually abstracts memory. So for example, if you think about the exec system call, it takes a file name, and in that file is basically the memory image of a program stored. It's text, some of it's global data, and that forms the memory of the application. Now the application can grow its memory, for example, by calling sbreak and extending its data segment. But it doesn't really have a direct access to physical memory. You can't just ask, I want, addresses, physical memory 1K to 2K. There's no way of getting at that. And again, the reason that there's no way that you can get at that is because the operating system wants to provide memory isolation and therefore wants to be in control or sort of intermediate between the applications and the physical hardware. And exec is sort of a system call that captures or shows that there's no direct access to the memory. Another example of this is like files. Files basically abstract away disk blocks. So instead of reading and writing the disk blocks of the disk that sits attached to your computer, that actually just not allowed in Unix. The only way to interact with the storage system is through files, and you can read and write files. You provide a convenient abstraction. You can name files, et cetera, et cetera. But then the operating system in itself can actually decide how to map those files to disk blocks and make sure that, for example, a disk block only shows up in one file, and that user A cannot actually manipulate or read and write the files of user B. And again, that sort of interface, that the file abstraction allows that sort of strong isolation between even different users and to different processes of the same user. And so you see that in some ways the system call interface or the Unix interface that you've been programming with in the util lab seems to be sort of carefully designed to abstract the resource in a way so that the operating system, the implementation of the interface, can actually multiplex the resources on multiple applications and provide strong isolation. Any questions about that?
We have a question in the chat that says, do more complex kernels try to reschedule processes on the same core to reduce cache misses?
Oh yeah, there's something called cache affinity. The schedulers in modern operating systems are very sophisticated, and indeed, try to avoid cache misses and things like that, to optimize the performance. And we'll see some of that much later in the semester. When we're going to be talking about like high performance networking, will show up there.
Another question from chat.
Yeah.
Where in XV6 can we see how the OS multiplexes processes?
There's a couple files that are relevant, but proc.c is probably the most relevant one. This will be a topic of a lecture in like 2 or 3 weeks. And we're going to go in great amount of detail and show exactly how the multiplexing happens. So one way to think about this lecture is a little bit of an introduction to a lot of different pieces, and because we got to start somewhere. Okay, so we go back into this picture here that I showed a little bit a while ago. We have this the shell running, the echo running, or not that picture. I want this picture here on this side. We've got the operating system, we have the applications running, and one thing we should be worried about is that the operating system should be defensive. And this is sort of an important mindset, that you have to get used to when you're sort of doing kernel development. The operating system, has to ensure that everything works out, and so it has to set up things up so that an app cannot crash the operating system. It would be too bad if an application that either by accident or maliciously passes, a tricky bad argument to the operating system, and the operating system would crash. And that basically means sort of denial of service for every other application. So the operating system has to be written in a way that it can deal and handle malicious applications. And in particular, another concern is that an application should not cannot break out of its isolation. The application might be definitely malicious, maybe written by an attacker, and the attacker probably would like to break out of the application, for example, and take control over the kernel. And once you have control over the kernel, then you can do anything, because the kernel is in control of all the hardware resources. And so the operating system has to be, or the kernel has to be written defensively, to avoid those kinds of things. This turns out to be very tricky to actually get right. In fact, even in Linux, there's still periodic bugs, kernel bugs or bugs that actually allow an application to exploit or to break out of its isolation domain and to take control. But it is a continuous concern, and we'd like to do as good job as possible. And this is sort of the mindset you have to have, when you're developing a kernel, that actually applications are perhaps malicious. Now, this means that there has to be strong isolation between the apps and the OS. And if the OS needs to be defensive and needs to be in a position that it can be defensive, there has to be sort of a strong wall between the applications so that the operating system can actually enforce whatever policies it wants to enforce. And this is typically done, a typical approach to achieving this strong isolation is using hardware support. And we'll give a little bit of flavor of that in this lecture, but we'll come back to it in much more detail in subsequent lectures. And there's sort of two parts of this hardware support. One is something that's called user kernel mode / kernel mode. In RISC-V, it's called supervisor mode, but it's the same thing. And then page tables or virtual memory. So all processors, all series processors that are intended to run an operating system and multiple applications have support for user kernel mode and virtual memory. It might be manifested or implemented in all slightly different ways, but basically all processors have it. And our RISC-V processor that we're using in this class has that support too. And so let me talk a little bit, I'm going to talk a little bit about user mode and kernel mode first, and then I'll talk a little bit about virtual memory. and mostly at the highest level possible, because there's a lot of important details, but I won't be able to cover those in this lecture. So let's first talk about user kernel mode. And basically what it means is that the processor has two modes of operation. One is user mode and the other one is kernel mode. And when running in kernel mode, the CPU can execute privileged instructions. I'll come back to in a second to those. When running in user mode, the CPU can only execute unprivileged instructions. And unprivileged instructions are the instructions you're well familiar with. Think about like add, sub, adding two registers together, subtracting two registers. So it's really basic, procedure calls, JR, all that kind of stuff. Branches, those are all unprivileged instructions that any user application is allowed to execute. Privileged instructions are instructions that basically are involved in manipulating the hardware directly, or setting up protections, and things like that. So for example, setting up a page table register, which we'll talk about later, or disabling clock interrupts. And so there's all kinds of sort of state on the processor that the operating system is tended to use, and manipulating that state is completely is done for privileged instructions. And so, for example, when a user application tries to actually execute a privileged instruction, then the processor just won't execute it, because if a privileged instruction in user mode is disallowed, and basically that will result in the transfer of control from user space, from user mode to kernel mode, so that then the operating system can actually take control and maybe kill the application because it's misbehaving. To get a little bit of a sense, the difference between the two in the privileged and unprivileged instructions, let me switch display for a second. And here on the right side of the display is a document, the RISC-V privileged architecture document. And that document contains all the privileged instructions. It's linked from the website under the references page. And in the next couple of weeks, or almost months, you will be playing around, with all these privileged instructions that are shown here. And in fact, many of them will, show up in some of them will actually show up in the next lecture in a great amount of detail. But you just think about this as there are privileged instructions that user applications should not be able to execute, and those can only be executed in kernel mode. So that's one aspect of this sort of hardware support for strong isolation. Yeah, Amanda, go ahead.
Just a quick question, like what I'm imagining in my head is something like, if kernel mode allow, else don't, like who is running that code and checking if it's kernel mode, and how do they know if it's in kernel mode? Is it like a flag or something?
Yeah, it's basically a flag in the processor. Literally there's a bit in the processor that says, user mode, one is, say, typically one is user mode and 0 is kernel mode. And so when the processor decodes an instruction, looks at the opcode, if the opcode is a privileged instruction and the bit is set to 1, it will deny executing that instruction. It's like a divide by 0. You're not allowed to do that.
Okay. But if that bit is changed, like if some way you were just able to overwrite that bit, then that's the only thing controlling.
Yeah, so what do you think, what the instruction that overwrites a bit, is that a privileged instruction or an unprivileged instruction? Is it a question? Clearly, the instruction that sets the bit must be a privileged instruction, because a user application should not be able to set the bit to kernel mode, correct? And then be able to actually run all kinds of privileged instructions. And so that bit is protected. Does that make sense?
Okay. Yeah.
Okay, good. So so that's user kernel mode, or at least the top view of user kernel mode. Turns out the RISC-V has a, as a number of you asked about, has a third mode called machine mode, we're mostly going to ignore that. So I'm not going to much say about it. Basically, it's one more level, because basically 3 levels of privileges instead of 2 levels of privileges. Amir, go ahead.
Hi, so I'm wondering, with respect to security, if all user code does go through the kernel, the intent is that things are secure. But is there a way for a user of the computer to completely go around the operating system?
No, not really. At least, you know, if done carefully, not. And if possible, like, you know, that might be the case that some programs have additional privileges that the operating system will respect. But those privileges are not given to every user. You know, for example, only the root user has certain privileges that allow you to do security sensitive operations.
What about BIOS? Does BIOS happen before OS or after?
Yeah, so the BIOS, this is the piece of software that basically comes with the computer, and that's booted first, and after the BIOS basically boots the operating system. So the BIOS is a trusted piece of code, and it better be correct and better be not malicious. Noah, go ahead.
Yeah, so you mentioned that the the instruction to set the kernel mode bit is a privileged instruction.
Yeah.
How would a user program ever then be able to get essentially have the kernel execute any kernel instructions if like the very instruction to access kernel mode is itself a privileged instruction? I guess it seems like there's immediately a barrier for a user program ever changing that bit.
Yeah, that's correct, and that's exactly the way we want it, correct? So one way to think about it, and this is not exactly how it works on the RISC-V, but like if you execute a privileged instruction in user space, or try to execute a privileged instruction in user I'm back. Sorry about that. Looked like my Zoom client crashed on me. I apologize for that. I don't really know why, but it did. Can everybody hear me again?
Yep, you're good.
All good.
All right. Well, there's somewhere a bug. Okay. So back to the second piece of hardware support, which almost all CPUs provide, which CPUs provide virtual memory. And I'm going to talk about this on Wednesday in much more detail. But basically, the processor has something, what is called a page table. And you've seen this a little bit, I think, in 004. And the page table basically maps virtual addresses to physical addresses. And the basic idea is to give every process its own page table. And in this way, the process can actually only use, or is only allowed to access that piece of physical memory that actually shows up in its page table. And so if the operating system sets the page tables up in a way that every process has disjoint, physical memory, then a process can't even access, somebody else's physical memory because it's not even in its page tables. So there's no way even to create an address or write down an address that will allow a process to access somebody else's physical memory. And so this gives us strong memory isolation. Basically, page table defines a view on memory, and every application or every user process has its own view of memory, independent of each other. And this gives us very strong memory isolation. And so now what we can do, if we can think a little bit in this way, then we can redraw the picture I had a little bit earlier, and just think about this as follows. We have a box, and ls sits in that box, and we have another box, and echo sits in that box. And that box basically has an address, a virtual address range starting from 0 to like whatever, some number 2 to the power, whatever the number is in RISC-V, which we'll talk about on, on Wednesday. And similarly, the address range for echo is, something, whatever, same to the power some x. And so ls has a memory location 0, echo has a location like 0, and you just completely separate it. And if the operating system maps those virtual addresses 0 to different pieces of physical addresses, then basically ls cannot access echo's memory and echo cannot access ls's memory. And similarly, the kernel actually, which sits below it, also has its own, at least in xv6, has its own address range, independent of the applications. And we can think about the user kernel mode as sort of sitting in between, a boundary that, things that actually run in user space run in user mode, and things that sit in the kernel run in kernel mode. And that's sort of the picture, that you should have, like the OS, sits there, sitting in kernel mode. And so this is the picture that you should have in your head. Now, as described so far, this picture is a little bit too strict. We have basically put everything in a box, but there's no way for one box to transfer control to another box. And clearly when that needs to happen, right? Because for example, ls, probably wants to call, read, the read system call, or write system call, or maybe, whatever, the shell wants to call fork or an exec. And so there has to be a way for an application or user application to transfer control in a coordinated manner to the kernel, so that the kernel can actually provide services. And so there's a plan, basically, in addition to this 2 pieces of hardware support that I talked about so far, is a way of a controlled way of entering the kernel. And it turns out, actually, on RISC-V, there is an instruction for this. It's called the eCall instruction. And the eCall instruction takes one argument, a number. And so in a user application that wants to transfer control into the kernel, basically can call the eCall instruction with a number, so like 2 or 3 or 4 or 5. And that number basically is the system call number that the application wants to invoke. And that basically what that does, it actually enters the kernel at a particular point or a particular location in the kernel that's controlled by the kernel. And as we'll see in xv6, in some later lectures, there's basically a single system call entry point, and every time an application calls eCall, and the application enters the kernel at that particular point. So one way to think about this is that if you have fork, the fork, call in user space, for example, the shell or your primes program called fork. Well, whenever it calls fork, it doesn't really call the operating system directly, the corresponding function in the kernel. Instead, what it does, it actually calls eCall with, the number for fork, which, and then that actually jumps into the kernel. So this is a kernel transition, and here's the user side, here's the kernel side. And then on the kernel side, there's a function called syscall in syscall.c, and that basically, every system call will end up at that particular system call function. And the system call will look at the number and then decide, and the number is actually passed in the register, I think it's A0, and the system call can look at that register, look at A0, see what the number is, and then, for example, call the fork system call. And so like, just to make it a little clear, so this is this hard boundary between the user and kernel. So the user cannot call, this fork directly. The only way, user application can actually invoke, the system call for fork is actually through this eCall instruction. And so I have another, if I have another, another system call, let's say write, it does something similar. The write system call cannot call the write code directly into the kernel. Instead, what it does, it calls what's these little wrappers are called system call stubs. It will call eCall, a function called write that actually executes the eCall instruction with the argument syswrite to indicate the write system call, and that again transfers control to syscall, and then syscall can actually demultiplex it to the write system call. There are two questions. Please go ahead.
So I think my hand was old.
Okay.
I can go ahead. The question I had was, how does or where does the kernel check for example, fork or write, if it is allowed or not? Right now, you're just passing in you're just calling eCall and the system call number. But where does the kernel basically decide whether this application should be able to invoke this particular kernel syscall?
Yeah, so great question. So in principle, on the kernel side, correct, when we actually this fork call runs, it can implement any security check it wants. It could look at the arguments, of the system call and decide whether actually the application should be allowed to execute the system call fork. Now, in Unix, any application can actually call fork, but let's say take write, write, needs to check whether the implementation of write needs to check whether the address that is actually passed into write actually is part of the user applications. And so that, the kernel is not tricked to writing data from somewhere else. It actually doesn't belong to the application. There are more hands, please ask.
Yeah, I had a quick question. So how does the kernel seize back control from a user application in the case where the user application is acting maliciously or it's in an infinite loop?
Yeah, so the plan for that, and again, we're going to talk about it in much more detail in a couple of weeks, is that the kernel actually programs the hardware to set a timer. And after the timer goes off, that will cause a transfer from user space to kernel mode. So at that point, the kernel is back in control, and then the kernel can reschedule the CPU to another process.
Okay, makes sense. Thank you.
Yeah, and we'll see that the exact details, we'll see in a little while. You have more questions?
Yeah, so this is more of a high-level question, but what drives the designers of an operating system's implementation to use a language like C?
Okay, so great question. C gives you a lot of control over hardware. And so for example, you need to program the timer chip. In C, that is actually easy to do because you get a lot of low-level control over any hardware resource, partly because you can cast anything to anything. So C is basically a very convenient programming language if you have to do very low-level programming, particularly interacting with hardware. It doesn't mean you can't do it in other languages, but this is historically the reason why C has been so successful.
I see. Thanks.
Why is C so much more popular than C++? Only for historic reasons in like these kinds of applications, or is there any other reason that like most OSs haven't adopted C++?
Yeah, so most operating systems, there are, I think, operating systems written in C++, totally possible. Probably the most ones that are not written in C++. And there are various reasons for it. You know, Linux is mostly C or no C++, and I think partially because Linus just doesn't like C++. Any other questions? Okay, so in this view of the world, right, where you know we have a way of transferring control into the operating system using system calls or this eCall instruction, and you know, so the kernel is now responsible for implementing actually the actual functions and ensuring you know, checking arguments and things like that to make sure that you know it's not being tricked in something doing something badly. And so in this view of the world, the kernel is sometimes called, you know, it's the trusted computing base. Sometimes called in security terms the TCB. And you know, basically, you know, what does it mean for it to be the trusted computing base? Well, it must be correct. You know, kernels must have no bugs. Because if there's a bug in the kernel, you know, the way to think about it is that maybe an attacker is able sort of to tickle that bug and turn the bug into an exploit. And, you know, that exploit may maybe allow that particular attacker to break out of isolation or maybe take control over the kernel. And so it's really important that, you know, the kernel really, you know, has to have as few bugs as possible. And basically the kernel, you know, must treat user apps, or applications or processes as malicious. And basically, as I said before, you know, basically the kernel designer should have sort of a security mindset, you know, when writing and implementing kernel code. And you know, it's hard to achieve this goal, right? We're having no bugs if the operating system is gigantically big. Is not that straightforward. And you know, almost every operating system, you know, that you use or is widely used, once in a while actually has a security bug. And you know, they get fixed over time, but basically, no matter what, there's always a new exploit at some point down the line. And you know, we'll see later why it's so tricky to get it all right. But you know, it's sort of understandable. Like you know, the kernel has to do tricky stuff. It has to manipulate hardware. It has to be very careful in its checking, and it's very easy to make a small slip up and, you know, have a bug. And so an interesting question, correct, is then, you know, what should run in kernel mode? Because it's really the kernel code that actually is in kernel mode that is the sensitive code, right? That is the trusted computing base. And one answer, you know, to that question is like, well, you know, we have our user kernel boundary. So here's user, here's kernel, and here's our applications running, and here is, you know, the program running in kernel mode. One option is to stick the whole operating system in kernel mode. So example, in most Unix operating systems, the whole Unix implementation runs inside of kernel mode. So for example, in x86, all the operating system services are basically in kernel mode. And this is called a monolithic kernel design. And you know, there's a couple things, a way to think about it. One, you know, it's probably not so good for bugs, right? Because any bug, you know, that you might have in a monolithic design, you know, might actually turn into an exploit, and that would be bad. So if we have a large operating system running inside of the kernel, it's likely that there are going to be more bugs. Like any statistics that you look up, it says like every 3,000 lines of code will have, you know, some small number of bugs. And so if you have many, many more lines of code and running in a kernel bug, you know, the probability or the chance that you have a serious bug, you know, goes up a little bit. And so the downside from the monolithic kernel design from a security perspective is there's a lot of code in the kernel. The plus, though, is, you know, typically, if you're thinking about an operating system, it contains of all kinds of different pieces. You know, you might have the file system piece, you might have the virtual memory piece, you might have, you know, processes, you know, and so there are all kinds of sort of sub-modules inside of the operating system that implement particular functionality. And the plus side of that is there's going to be tight integration possible between these different sub-modules if they're all sitting in the same program. And that can actually lead, you know, to great performance. For example, if you look at an operating system on Linux, it actually achieves very impressive performance. And so this is one sort of one design. Another design, which basically focuses on reducing the amount of code in the kernel, is what's called a microkernel design. And in this design, the goal is actually to run as few lines as possible in kernel mode. And so, for example, there is something of a kernel, but the kernel has very few components to it. So, for example, it typically has some form of IPC or message passing, a little bit of VM support, very minimal, basically only the thing necessary for page tables, and something to multiplex different CPUs. So some multiplexing code. But generally the goal is to run the bulk of the operating system outside of the kernel. And so, for example, again, as we have our boundary here, what we'll do is actually we'll run other parts of the kernel as normal user applications. So, for example, we might have an we might have a user process. Oops, still okay. That's not what I intended, but it doesn't really matter. You know, that's the file server. And so, and the file server is just in regular user space. So user space, kernel. So even though I drew it by accident in red, I intended to draw it in black, the file system might run like a user application, like, you know, Echo, you know, the shell, they're all run in user space. And we might have other, you know, user applications like the parts of the VM system might actually run as a regular user application in user mode. And so this is sort of a nice design, correct? Because, you know, the amount of code that presumably that's in the kernel is small. It's small, and small means hopefully fewer bugs. The one issue, you know, of course, is like, you know, we have to arrange that the shell can talk to the file system. For example, you know, the shell calls exec, and there has to be a way of actually getting to the file system. And so typically the way that works is that the shell will send a message, you know, through the IPC system to the kernel. The kernel will look at it and say like, oh, you know, this is intended for the file system. So the file system sends it to the file system. The file system doesn't work, you know, sends a message back saying like, you know, here's the results of your exec system call, and then, you know, sends it back to the shell. And so these are typically implemented using messages. And so for any interaction with the file server, now you have to jump once into the kernel, once out of the kernel, once into the kernel, once out of the kernel. And if you compare that with the previous design, like if this guy wants to talk to the file system, it's one system call in and one basically call back out. And so you double the number of system call entries. And so one typical problem or challenge with often with the microkernel approach is actually how to achieve good performance. And it has sort of two components to it. One, you know, just jumping back and forth, you know, between user mode and kernel mode to actually get something done. And the second part is because, you know, the different pieces are really well isolated from each other, a tight integration is less, you know, more complicated to arrange than, for example, in the monolithic kernel, where basically everybody can, you know, for example, the file system and the virtual memory system can easily share a page cache, which is a little bit harder, you know, to achieve in the microkernel design, and therefore it's sometimes more difficult to get high performance. Now, these distinctions, you know, between microkernel and monokernel are very high level. So in practice, both types of kernel designs show up. Most desktop operating systems are typically monolithic systems, mostly for historical reasons. A lot of the, if you run very intense, you know, OS intense applications, for example, in a data center, they typically run on a monolithic kernel. mostly because, for example, Linux provides great performance, but many, for example, in embedding settings, like Minix or Cell 4, those all tend to be microkernel designs. And so both designs are popular. If you probably start a new operating system from scratch, you probably start with, you may start with a microkernel design. Once you have a monolithic design, like for example Linux, it's going to be would be a ton of work to rewrite it into a microkernel design, and that's maybe just not conducive to the incentives. People probably want to spend rather time implementing new features than actually restructuring their kernel. And so these are sort of the two main designs. As you know, x86 it falls in the monolithic design, as most classic Unix systems do. But later in the semester, we'll talk a lot more in detail about some of the microkernel designs. Any questions about this? Because this was a hot topic in the email questions. Okay. Okay, so let me switch a little bit. I'm going to switch to some code and sort of see how all this plays out in XV6. So here's two windows, and you're an Emacs window with like the proc structure. And the first thing I want to do is look a little bit at the code base. You've probably already done this, but you see that the code is sort of organized around three parts. One, the kernel, and then looking at the kernel, that basically includes all the kernel files. And so XV6 being a monolithic kernel, basically all these programs are compiled into a single binary called the kernel, and that's actually what we run in kernel mode. And then there's user, and those are basically the programs that run in user mode. And this is why one is called kernel, and the other called user. And then there's one more program called makefs, which actually builds an empty file system image that we're stored on disk, so that we can get off the ground with an empty file system. Okay, so let me switch back again to, I want to say a little bit about how the kernel is compiled, because you probably have seen this and might not really have realized it, and it's sort of important to understand. So when the construction of the kernel, the make file basically takes one of these C files like proc.c, invokes the GCC, the CC compiler that generates a file called proc.s that goes to the assembler, and this is basically a RISC-V assembly, and that actually produces a file called proc.o. And basically, that's the binary version of the assembler. So it's, and the make file does this for all files of the kernel. So, for example, pipe is another one. Same story. GCC compiles into pipe.s, and goes through the assembler, and we get a pipe.o. And basically, then the loader takes all these .o files from all the different files and links them together and produces the kernel. And that is actually then what we run. And for your convenience, the make file also produces a file called kernel.asm that has the complete kernel disassembled, and you can just look at it, and that helps later on when you have kernel bugs, and it's easy to see which instruction was executed at the point you got the bug. So for example, if I look here, kernel.asm, we see that here's the kernel file with assembly instructions. And one thing you note, for example, is that the first instruction is located at this address 800000, and that is in whatever AUPC instruction, the RISC-V instruction. And anybody knows what this is? The 00A117 or the 83103 is 6505. Anyone who wants to answer that question?
That's the text version of the assembly instructions on the right?
Yeah, exactly. So what here on the 00A117 is exactly the same thing as the symbolic, the textual version of that, AUPC. And so basically this is the binary encoding of the actual instruction. Right? And every instruction has a binary encoding, and the kernel.asm file actually shows those binary encodings. And this is sometimes convenient when you look at the GDB and you want to know what actually is going on. You can see actually what the binary encoding is. Okay. Okay, so then when we run XV6, I'm going to run it inside of, actually let me first run it without the GDB. We'll compile a bunch of stuff, and then it invokes QEMU. Right? And this is basically a C program that simulates or emulates a RISC-V processor. And you can see here in the -kernel flag, it actually passes the kernel as the program to be run inside of QEMU. And QEMU and the kernel agree that basically the starting place for any program is this address 80000. And we see that we pass a couple other flags to QEMU. It says M, that's the amount of memory that the machine, this virtual machine has, this virtual RISC-V machine. It passes in how many cores there are. It passes in the machine, the disk drive, which contains the file fs.image. And so basically a bunch of things are sort of set up to make QEMU behave like a real computer. And so one way, when you think about QEMU, you really should not think about it as a C program. Really the way you should think about it is as follows. You should think about it as this, namely a real board. So for example, on the left, this is a RISC-V board. Actually, there's a RISC-V board that sits in my office, and it can boot more or less XV6. And so when you're running, QEMU with your kernel, you should think about it that actually you're running it on this board. And the board has an on-off button. Here's actually the RISC-V processor. There's room for peripherals. So for example, one of these connectors is a connector for Ethernet. One is the PCIe slots. There's some RAM chips on the board. I don't exactly know where they are, but there are. And so this is sort of that's the physical hardware, the computer that you're programming. So XV6 manages this board. And that's the picture you should have in your head. And in fact, if you sort of zoom in, you can find all the documentation of like what actually sits inside of this. And inside of this, inside of this RISC-V processor, the schema for the RISC-V processor is shown in this picture here. And we see here, for example, there are multiple cores. And in fact, there are 4 cores. There's an L2 cache. There's a connector to DRAM. There's a bunch of ways to connect to the outside world. So for example, here's UART0, and UART0 is actually connected on one end, to the keyboard, and to the other end to the display. And there's some ways to actually get clocks going, which I'll talk about in much more detail later. But these are all the components that basically, the XV6 and things that you will be modifying to interact with actually the real hardware. And in fact, the computer system or the computer board that actually is emulated by QEMU is pretty close, minor some small details to this particular computer board, which is made by SiFi. And unfortunately, I can't show you the real thing. As I said, it sits in my office, and I haven't been in my office since March, probably collecting a lot of dust. But it's important to keep in your head, when you're running QEMU, you're running basically on real hardware, and it just happens to be implemented in software. Does that make sense? Pause for a second here. So let me say a little bit more about it. So what does it mean for QEMU to emulate a RISC-V processor? Well, literally, if you think about it, as I said, QEMU is a C program. It's an open source C program. It's a big program. You can actually just, download it or git clone it. But internally into C, it is basically a for loop, an infinite for loop, that basically does nothing else than read instruction, the RISC-V instruction, basically reads, 4 bytes or 8 bytes, and basically looks at the bits in that instruction and decodes them, figures out what the opcode is. And we saw, like, for some of the instructions, the binary version of those instructions in that .asm file. And so it decodes the instruction. So for example, maybe it will decide this is an add instruction, or it's a sub instruction, RISC-V sub instruction. And then basically it executes the instruction in software. And that basically is all what it does. For every core, it runs this particular loop. And in addition to doing this loop, it has to maintain some state. So it maintains state for all the registers. So it has a C declaration for like X0, register 0, X1, etc. And so basically when it executes an instruction, for example, the instruction is like whatever, add, A0, 1 to 7 and store it in A0, then basically it takes the constant 7 and 1, adds them up and sticks it in A0. Right, so for example, stores the 7 here. And then executes the next instruction and keeps going, keeps going. In addition to basically emulating or correctly all the unprivileged instructions, it also emulates all the privileged instructions. So that's in essence what QEMU does. But the best picture for you to have in your head is that basically you're running on a real physical RISC-V processor, like the ones you have probably, many of you have implemented one, I think, in 004. Any questions about this?
Hi, yeah, I was wondering if it does any hardware tricks, so like overlapping instructions or anything?
No, it runs on a real processor below it, correct? So when you run QEMU, it runs probably on an x86 processor. That x86 processor does all kinds of tricks, to pipeline instructions and things like that, right? So the way to think about QEMU, it's just a C program.
Makes sense, thank you.
What about multi-threading? So if the QEMU supports, you said 4 cores, or does it only support 1? And if that case, does it have actually multiple threads running it?
Yeah, so actually the QEMU that we use on Athena, and probably the ones that you actually download, they will use multiple threads internally. So QEMU internally use it to get parallelism. So in fact, these 4 cores that are being emulated are sort of being emulated in parallel. And we'll see that in one of the labs later, how that plays out. So definitely there's sort of real parallelism going on between the different cores. Okay, so I'm gonna do a little bit of walking through XV6 to get a little bit of sense what the layout of the land is. And in later lectures again, we're gonna go in much more detail. So I'm gonna fire up QEMU under with GDB support. So basically QEMU has inside of it a GDB server. And so it starts it up and then it just waits, for GDB to connect to that. So I'm going to start here on my computer. This is a RISC-64 Linux GNU GDB. On some of your machines, it might be multi-arch or something else. But basically, the GDB compiled for RISC-64, RISC-V 64. And I'm going to set a breakpoint at entry because that's the first, we know that's roughly the first instruction that actually where QEMU is going to jump to. So I set the breakpoint, I run. And basically, it doesn't actually break exactly at 8000, but at 0A. And if we look here on the right, we see that 0A is reading the control system register mHardID and loading that value into A1. And so basically, QEMU simulates that instruction, and we can execute that instruction, and we go to the next instruction. And basically, this address 8000 is just basically something that was agreed on, by QEMU, or QEMU told, basically says, like, if you want to use QEMU, the first instruction we're going to jump to is at that particular location. And we basically arranged for the kernel loader to load the kernel of that program. So there's a file kernel LD that basically specifies how the kernel should be loaded. And you see here that basically the first address that the kernel is going to use is actually that particular address that basically QEMU specified. And this is how we get off the ground. Does that make sense? Okay. And we see also that here actually GDB shows the binary encoding of the instructions. And so we see that basically, I guess the CSRR is a 4-byte instruction and ADI is a 2-byte instruction. Okay, so I'm going to see, basically, so x86 basically starts at entry.s. And we have no paging, we have no isolation, and in fact, it starts in M mode. The x86 jumps as quickly as possible to kernel mode or supervisor mode, as called in RISC-V. I'm just going to set a breakpoint at main, which actually runs in supervisor mode. So I'm going to run there, and then I get to the first instruction of main. So let me show this. Here's main, and I'd like to run GDB in this layout split mode. And so you can see in GDB actually what the next instruction is being executed. So you see there's a breakpoint at that particular instruction. Since this is I ran QEMU with one CPU, this makes the GDB a little bit easier. So there's now only one core active. So QEMU emulates only one single core, and I can step through that. And so I can go to the next instruction, and that calls a function called console init, which does exactly what you imagine it does. It actually sets up the console. And so once we set up the console, we can actually print to it. And so you'll see in a second, we'll get a new line, and we get x86 booting. Okay, so and there's a whole bunch of additional code to set things up. There's setting up the page allocator, setting up virtual memory, which I'll talk about on Wednesday, loading, actually turning paging on, which I'll also talk about on Wednesday, setting up the initial processes or setting the process table, setting up code to do the user to kernel transition, setting up the interrupt control, the PLIC. We'll talk about when we talk about interrupts, but this is one thing that we're going to be using to basically talk to the disk or talk to the console using interrupts. It sets up the file system, it allocates a buffer cache, initializes the inode cache, initializes the file system, initializes the disk, and then basically once all sort of things are set up, when the operating system is running, it's going to start running the first process. And this is the user init. So this is a little bit of interesting. So I'm going to go to user init for a second, and I'm going to single step there. Before continuing, any questions about this?
Is there a specific order in which the setup functions need to be called?
Yes. Some functions must be run after other functions, and they're in particular in their, some of them doesn't matter, but for a few of them, yeah, it's important that they run after other ones. Good point. Okay, let me go to, so here's user init. And basically user init is a little bit of glue code or initialization code to sort of take advantage of all the general infrastructure that x86 had to basically get the first process of the ground. x86 needs some image, right? We can't run the file system really yet or do exec. And so the x86 needs sort of a small little program to sort of get off the ground. And that small little program is init code. And the binary version of that program is actually linked or declared statically into the kernel. And in fact, that code corresponds to this particular user program. It's a little program written in assembly, and basically it loads the address of init into A0, it loads the address of argv into A1, and then it loads the number for this exec system call into A7, and then look at here, it calls ecall. So basically what init does is like running 3 instructions and then running the 4th instruction to basically transfer back control to the operating system. So for example, if I set a breakpoint in syscall, and I keep running, then basically, user init, will create the initial process, return to user space, run these 3 instructions or 4 instructions, and basically come back into kernel space. And so basically, this is the first system call that any user application in x86 runs. So let's see what happens if I'm right. So we're going to continue, and we actually got to syscall. So if we can syscall, we can look at it. It's a function at the bottom. And so we're back into kernel space now, and we can sort of walk through and see actually what happens exactly in syscall. So I'm going to single step a little bit. It looks up what the process is that's in it, that pulls out the system call number that's used. So we can now print num, and we'll see that's 7. And if we look at, user or the kernel syscall.h, that declares all the system call numbers. And we see 7, that is indeed system call exec. And so basically this tells the kernel that, some user application called an eCall instruction, and with the intention of calling the system call for, with the intention of running the exec system call. And so we can single step a little bit further. We go to the next thing. This is the line that executes the system call. So let's go there. And you see that basically the number is used to index into an array, and the array has a bunch of function pointers, and presumably the sysexec entry, points to the sysexec function. So we're going to single step into this, and we see that we're actually at the sysexec. So this is in sysfile. We can look at it a little bit more in a bigger window, and we basically see here the system call. And the first thing that you see is it actually gets arguments from user space. So it gets the path name. So we can jump a little bit further. Memset, boom, boom. Let's basically allocates space for arguments, copies all the arguments from user space to kernel space. We'll look at that in great amount of detail in a couple of weeks, so don't worry about it too much yet. But basically, there's some code to move arguments from user space to kernel space, from the user address space to the kernel address space. And if we now look at path, we can print the path, hopefully, and we'll see actually that that is a string, and we'll see that basically what that little init code program does is trying to exec, the init program, which is yet another, program. So let's look at that for a second just to see what that is. So here we have init, and init basically sets up a couple things just for user space. It opens the console, the file descriptor for the console, it dubs it, a couple times, calls fork, and basically the first thing it does, actually, it tries to create a new process, and it will exec the shell. And so this will, in the end, result as the shell being run. So for example, if I would continue, I probably break again in sysexec, and if I would look at the arguments, I will see that actually the exec system call is being called to exec the shell. And once we exec the shell, let's do that. Then we'll do a couple more system calls, and at some point we'll see the, let me continue, then basically the shell starts running. And so that gives you a little bit of a sense, actually how x86 gets off the ground, how the first shell actually gets to run. And we saw the sort of a little bit of an overview about how the first, when the first system call actually happened. We haven't really looked at the detailed machinery for these system calls, now how they get in and out of the kernel. We're going to talk about it in a couple of weeks or 2 weeks in lecture in a great amount of detail. But this is sort of enough for you to understand actually how to do the syscall lab, that we assigned for this week. And so these are sort of the pieces that you will be interacting with. Any questions before I wrap up, because we're almost out of time? Feel free to fire away.
Are we going to do anything with networks or like networking in the labs?
Yes, the last lab is you will implement a network driver. And so you will write the code that interacts with the hardware, and you have to manipulate the registers of the network driver over the network card. that basically connects, to this RISC-V board. You saw that there was a plug basically to plug in an Ethernet control cable. And so there's an Ethernet card. And so you're going to be programming that card, and you're going to actually send some packets across the internet.
Great, thanks.
Yeah, that's the last lab. Any other questions? Okay, let me wrap up here. I think the system call lab itself, because we're not really going great amount of detail, hopefully shouldn't be too bad. Might be easier than the util lab. Next lab, however, might be more difficult. So it's always hard to get all these labs right. But the Cisco lab hopefully shouldn't be too difficult. But please don't wait until the night before. Get going early, so that if you're running some obscure bug, that we can actually help you out and make sure that your program works in the end. With that, I'll sign off, and I'll see you in Wednesday.